Hello, everybody. Thanks for having me at this conference and to talk to you. Very privileged, thank you. What I'm going to be talking to you about is a set of ideas that are somewhat connected, and my goal is to get you to, or to try to encourage you to think about data types in an algebraic way, and to explore parametricity, and hopefully I'll have some time. We can talk about optics at the end. So let me just get some things going. There we go. So, okay. So a little bit about me. I work for a company called Simple Machines, a great company based in Sydney, Australia. I live in Brisbane, Australia. That's a little bit further north of Sydney. Yeah, so I write code 40 hours a week. That's my full-time job. And as Sandra mentioned, I am also a flight instructor. I do that for about 20 hours a week. On the weekends and so on. And I could tell you some stories there. So I work for Simple Machines. So let's get started. We begin with a premise, and that premise is very simply that we are functional programming. And I want to point that out because some of the ideas that I'm going to present to you, if you're not familiar with or you're not thinking about it in terms of functional programming, you may sort of raise an objection because we are not functional programming. And so some of the things that I might talk about don't make sense unless you are functional programming. And not only that, we've probably all seen the opposite of functional programming. I've certainly seen it. It's called dysfunctional programming, bit of a play on words. But when I say functional programming, I mean the standard definition where in program expressions we can replace the expression with the value without altering the program. So that's what I mean by functional programming when we're talking about it. So let us talk about just data types and the algebraic representation. You may have heard of algebraic data types before. And what I want to do is talk about the algebraic representation. So let's just think about, I want you to think about, just go back to, primary school algebra, where we could add two numbers. So for example, when we talk about the either data type in Scala or many other programming languages, we're talking about addition or sum types. We're adding A and B. So either A and B is the sum of A and B. When you are talking about it colloquially, you probably use the word or. So you'd say A or B. We also have product types, which is A and B. And we're talking about multiplication there. So that's what we mean by product types. It's the product of A and B. And furthermore, we have exponentiation. So these are just some sort of base facts to lay down here. If we have a function that takes an element from the set A and returns an element from the set B, then we are taking B to the power of A. And I'll explain what that means in just a moment. We also have just some simple primitives such as the value 1, also called unit sometimes, and or void or nothing. It's sometimes, I think it's called in Scala, which is the value 0. So when we have just these basic building blocks in algebra, we can do some things with them. We could do 1 times 1, for example, or we could do 1 times 1 plus 1, and so on. These are the basic building blocks of algebra and algebraic data types. So let's just have a look at a really simple one, which is a Boolean. So it has two constructors, true and false, and as arguments, they take nothing. When a constructor takes nothing, that is the same thing as taking unit. And it is fair to say that a Boolean is 1 or 1. so true or false, and therefore it is 2. And the mindset that I want you to get into is I want you to imagine I'm thinking of a Boolean, but I'm not telling you what it is. You would require 2 guesses before you could be certain that you've guessed what it is, because Boolean is 2. So let's have a look at another data type, option. I think most people who have written Scala have seen this data type. But unlike Boolean, it's parameterized over a type parameter A. So that A is a free variable in the algebraic expression. And if we look at its constructors, we have the none constructor that takes no arguments. That's the same as taking unit. And we have another constructor, sum, that takes an A, which leaves us with the algebraic value 1 plus A, where A is free. Let's imagine, for example, I said to you, I'm thinking of an option of Boolean, but what I've just said to you is 1 plus 2, and therefore 3. So there are 3 possible values of that data type, option Boolean. We don't know how many values of the type option there are until we know A, or how many values there are for A, because it's free. Just another one to look at. If I said to you, please construct a value of the type either void or A, where void is 0, you would be able to do that the exact number of times that you could construct A. And that is to say, I have simply done 0 plus A. And we can drop the 0 plus, of course, because that's an identity for A. So this is the algebraic mindset to get into when we're examining data types. I'm really going to emphasize this point, by the way. If I said to you, construct a value of the type void and A, what I've said to you is 0 times A, and therefore 0, you would not be able to do that. There are no values that have that data type. And I'm hoping to sort of push the intuition that, like challenge yourself and try to understand why you cannot construct something of that type. It's because you cannot get a void, and therefore you cannot get a void and an A. Or in other words, 0 times anything is always 0. You can never construct one. This is just an interesting little fact. At some point in your life, you've probably realized, I did at one point, that 2 times 2 is equal to 2 plus 2 is equal to 2 to the power of 2. These are all 4. And what I mean by that is, so 2 times 2, the product there, 2 plus 2, the sum, and 2 to the power of 2. So that is the return type to the power of the argument type. These are all 4. Now that is to say, if I said to you, I am thinking of a function and its type is Boolean to Boolean, there are only 4 possible things that have that type. So I must be thinking of one of 4 possible things. And it's a really good exercise to list out all those 4 functions. And I encourage you to try. I can tell you what they are because I don't have them in the slide here. There's the one that returns its argument, so the identity. There's the one that negates its argument. There's the one that always returns true, and there's the one that it always returns false. There are no other functions with that type. And just going back to when I said, assume we are functional programming, if we were not, you could probably see an objection that could be raised there. For example, someone might say, given the Boolean, start a thread or something like that, or, print hello, and then return the argument. This is a different function. However, we have violated the premise of functional programming when we do that. So that's why it's important to put that stake in the ground there, that we are functional programming. It gives us the number of inhabitants. So that's what I mean when I say, the number of values with that type. These are called inhabitants. So, a pair of Boolean has 4 inhabitants. Let's look at some more, a little bit more complicated one, just to prove that we can do it. So option of a function Boolean to maybe Boolean is 1 plus, and then parenthesis, English doesn't have parenthesis, a pause perhaps, 1 plus pause, 1 plus 2 squared, which is not 9, it's 10. Haha. Yeah, so that's 10 inhabitants, right? So this type here has 10 inhabitants. And just to sort of really exaggerate, I just came up with something crazy there. There are 40 of those. It's not a very useful data type that you're looking at there, probably, but that is 40 if you calculate that expression there. So this is the mindset to get into when we're reasoning algebraically about data types. Now, I want to talk about lists in particular for algebra, and that's because lists are defined recursively. So the definition of a list includes a list itself. You may think of a list of A as either 0 A's or 1 A or 2 A's, and notice I'm using the word or there. So these are just sums. So A to the power of 0 plus A to the power of 1 plus A to the power of 2. Or, when I say A to the power of 2, I mean a pair of A's, the product of 2 A's. And we can simplify that using algebraic rules, just straightforward algebraic rules, to 1 plus A times list of A. But if we did say 1 plus A times list of A, we've given itself in the definition. So that is to say a list of A is 1 plus A times list of A, and we end up with recursion. You can think of it intuitively by the constructors. So nil, the nil constructor that carries unit, that's 1, or, and that's plus, the cons constructor, which carries an A and a list of A, a product of those two things. So let's really emphasize this idea of algebra in data types. Now, does anyone remember calculus? I'm sure some of you use it more regularly than I do. Oops, I pressed the wrong button. But I don't quite remember calculus either. So whenever I talk about it, I kind of have to remember. So here's a data type. It's either 1x or a pair of 2x's. And algebraically, that is x plus the product of 2x's. So just to sort of go over that again, either being plus, so it's plus between the left side and the right side, and the tuple there being a product of 2x's. So x plus x times x. And we can differentiate this equation with respect to x, or we can take the partial derivative. So let's do that. So we apply the sum rule, and we end up with, what you see there. I won't try and pronounce it. But the final result there is that we end up with 1 plus 2 times x on that data type. In other words, an option of a pair of Boolean, so Boolean being 2, times x. And this is quite an interesting insight in terms of data type design when we take the derivative of a data type. So the partial derivative of either x or pair of x's with respect to x is 1 plus 2 times x. The reason it's an interesting insight is it relates to something called zippers or one-hole contexts, where it gives you a context within the data type. So that is to say, if I were to go and stand on one of those x's in the data type, what would I see around me? What would be my context? I would see one of 2 x's, which can be denoted by that Boolean, or I'd see what would I see? 1x. I'd see either 1x to my left, 1x to my right, or I'd be standing on the end. Hopefully, I'm drawing a bit of a picture in your mind. It's a little bit difficult, I know. So let's do another one, just a little bit more complicated. So we have a pair, so a product of x plus x. So it's x plus x squared, essentially. So there it is as an algebraic expression. We're going to differentiate it with respect to x, and we end up with 8 times x. So we need a data type that denotes 8. We can get that by 3 Booleans as a product. No, we can get that by 2 to the power of 3. That'll do it. So Boolean, arrow, option Boolean times x. 2 to the power of 3. Oh yeah, that's 8 as well. Yeah. Derivative of that expression or that data type with respect to x is, I've denoted it that way. So option Boolean, arrow Boolean, or 2 to the power of 3 times x. Here's a much simpler one, which kind of emphasizes the one-hole contextness of it. So just 3 x's, x times x times x. If we differentiate that with respect to x, we end up with 3 times x squared, which I'm sure you'll remember from when you did study calculus. So we know what 3 is. 3 is option Boolean, and x squared is a pair of x's. So let's just think about that. I have an option Boolean times, so and 2 x's. And so if I were to just sort of go back to this data type and just point to one of the x's, and then say, well, if you were standing where one of those x's is and looked around, what would you see? So for example, if you were standing on this x, you would see 2 x's to your right, or over to this direction here. If you were standing on this x, you'd see that one on either side of you. And if you were standing on the end one, you'd see the other 2 to the side. In other words, you always can see 2 x's. You just need to know which x you are standing on. Or in other words, which of the 3 positions you are on, as well as 2 x's. So if you hold that thought, which of the 3 positions you are on, and 2 x's. So the derivative is the one-hole context for the type. So this is just a brief summary of what we just did. We can differentiate our types or our algebraic expressions. Let's do list. Now, as we said earlier, lists are defined recursively. So I'm just checking on the time, see how much longer I've got. So it gets a bit tricky, right? So we end up with that same equation. List of A is 1 plus A times the list of A. But, 1 plus A times the list of A. And if you just sort of, if I kind of can skip over this a little bit, but also just note, all I'm doing is applying standard regular algebraic rules, just those you would get out of a mathematics textbook in chapter 2 or something like that. There's nothing tricky going on here. I subtract A times list of A from both sides. Then I get this equals to 1. Multiply by 1 here, and then take the distributive law. We end up with list of A is equal to 1 divided by 1 minus A. And by doing this, what we've done is we've removed the recursion in the definition. But there's a catch, and the catch is we've ended up with a quotient or a division and a subtraction. And I've not told you anything about that in terms of algebraic representation for a data type. So fortunately, we don't have to care when we take the derivative. When we take the derivative, this is simply just using a variable u in taking the derivative, so we can apply the rules much easier. We end up with the derivative of a list with respect to A is minus 1 over, actually I think it's on the next slide that I'm thinking of, yeah. So we end up with the derivative of 1 minus A, or 1 over 1 minus A is equal to this expression here. And what we can then do is simply substitute back in for that variable that we set u, multiply both sides, or multiply the right side by -1, apply the exponent rule from calculus, and we end up with the derivative of a list of A, which is what we have here. This is a list of A, is a pair of list of A's. All right, so you can see here, this expression here, actually, I think there might be a typo there because it should be 1 over 1 minus A. Oh, it is, yeah, -1. Sorry, there's no typo. So this here being a list, we end up with list squared. And if you think about what a list is, and with respect to A, and you go and stand on one of those elements in the list, and you try to, understand the context, you will see that you have a list on either side of you. You have a pair of lists, essentially. So again, we've derived the one whole context. Now that was a little bit of a rabbit hole, a little bit of algebraic reasoning about data types. Most of it is just to get you to think about algebraic, or think about data types in an algebraic way. And I kind of want to emphasize this. Here is some code that I came across recently with the identifier names changed. You can even think about this data type algebraically. I won't explain how, but I just want to gain your trust that I can do it if I wanted to, which raises the obvious question, why do I want to? And I just want you to hold that question. There is a good answer. So before we get to that answer, let's talk about parametricity for a moment. So parametricity is very similar. Is very similar in the reasoning or the exercise that we just did. And I've even used Java. I use Java here just to emphasize that you can even do it in Java, right? So here we have a function that takes a Boolean and returns a Boolean. There are 4, right? That's 2 to the power of 2, just using straight algebra. This one here, when we use types, in this case, takes a string and returns a string, from a practical point of view, how much extra knowledge have we gained by using those types? And I think the answer is not very much. Was there really any point in using types? The reason being, it's string to the power of string, which is huge. We started off with a large number and we've ended up with a large number. We've not really constrained much there. So let's have a look at this data type, this function type here. So it's generic in A, and it says it takes an A and it returns an A. And we might ask the question, how constrained now is this type? Now, normally when I'm giving these talks, when we're not confined to our office rooms, I can see your faces, and I can usually, there's usually someone in the audience and they're a little bit suspicious, what's going on here, because the answer is 1. And, some people might not believe me just yet. And so I'm going to assume that you have that, at least a few of you are a little bit suspicious when I claim that there is only one program that has this type. So, and by that I mean, if you were to come up to the comment that you see there hidden from view and put whatever you want there, as long as you don't change the type, you only have one choice to put there. There's only one thing you can do. That thing is return the argument. It's a good challenge to try to see why that is true, or try to make it false and see that you can't make it false. And you can even write a proof. I actually did write a proof in Scala last week. I'll have to go and find it if you're interested. I'll show it to you after the talk. It'll be somewhere on my disk. But what the important point is here, we have used a polymorphic value. So instead of using Booleans and strings and so on, we use a polymorphic value, and we gain a lot of knowledge about what that function does. To the point of totality in this case, we know that the only thing that it could do. And we can calculate that. Similarly to how we calculated Boolean as 2 and so on, I can actually calculate this value here, and that would be the proof, to be 1. So this is what I'm trying to establish here is there's a reason we use a lot of polymorphism, because I'm going to show you optics. The idea of using the polymorphism to determine the function's behavior is called parametricity, or theorems for free. It was originally discussed by Phil Wadler in 1989. Basically, you write down the definition of a polymorphic function or the type, and you don't show the implementation. And Phil, in this case, will tell you a theorem that the function is satisfied. Just to give another example, if we have a list of string, there's no polymorphism there. There's not much that we know about it. And so since there's no polymorphism, there's no tricks to do. The answer to how many possible things have this type is huge. And it's so huge that, if I were to write a function of this type, I'd stop and think, do I really want to do that? Because I've not really utilized the types very well. However, if you look at this type, given a list of polymorphic T returning a list of polymorphic T, I can give you a theorem. And that theorem is every element in the resulting list appears in the input. So I want you to be like as malicious as you can to try and make this statement false. My claim is you can't. No matter what you write in here for this function, this theorem will always hold. So again, you might be suspicious that that may not be true. That's okay. It's a good exercise to try to see why it is true and try to make it not true. You won't be able to. But we've not gained total information about what the function does. There are many things it could do. It could rearrange the elements in the list. It could reverse the list. It could leave the list alone. It could delete some elements. There's all sorts of things it could do. So I had to write Haskell here just due to some space, but this is pretty easy to understand. It basically says, this is an automated test, and it says for all values, alpha character values, x, then calling my function with a list holding a single element will always return the same list. So that is to say, if you put in a single element list, you'll always get the same list back. This one here is a little bit more complicated, and it says that for given any two lists, x and y, then if I append x and y and then call my function, that's the same as calling my function on y and then appending calling my function on x. Now that I've done that, I do now know what that function does. It must reverse the list. That's the only thing it can do, given those two tests. So a question I regularly receive is, polymorphism, it's really hard to read. Why do you do it? My answer to that question is because it's much harder to read otherwise, because I don't know what the function does by the type anymore. And then a second objection that comes up is, yeah, but types don't tell you everything about what the function does. And this is true, in which case this is the solution to that. We would write some properties. And what properties do, so types provide the proof of the proposition. They say that type is true, whereas tests provide failed negative proof. So it'll just plug lots of lists in there and make sure it can't fail it. And that is essentially the only difference between types and tests. Right, I don't know how much more time I've got. Do you know how much more time I've got, Sandra?
Yeah, you can still speak. We are a little bit delayed, so it's okay.
Okay, cool. Okay, so I hopefully I've got you in the right mindset to talk about optics, which is an idea that, or a data type essentially, that is incredibly useful in terms of its practical application. I've been writing Scala code lately, on and off for the last 6 months. And every single time I've come across this Scala code, I have seen code that could benefit immensely by the use of optics. So that's my real goal here. That's what I'm trying to do. I'm trying to get this idea across. because if you don't take advantage of optics, you end up with a lot of code repetition, and quite a lot. It's very subtle though, so it's not obvious that the code is repetitious. But I've seen code bases of thousands of lines of code, and all it is a re-implementation of the optics library across thousands and thousands of lines. And if I can save anyone from writing that code over and over again, then my job's done. So what I'm going to do is I'm going to provide you, first of all, a definition of an optic. Now, by definition, I mean, I'm thinking back to the monad tutorials of 10, 15 years ago, where people would say, monads are, I can't remember what it is, category in the end. I can't even remember what it is, but some weird some definition that is a correct definition. Apologies for not remembering that. I probably should, but it's a correct definition, but it's not a very satisfying definition. It's not something that you can just straight up start using if you're coming at it from from basics. If you've not read any category theory, and I want to try to do similar for optics. So I want to give you a satisfying definition. And also, if you go back to the monad tutorials, you'll find that a lot of them are, in fact, incorrect, and therefore, not very helpful. They make you feel good, but they're not very helpful. So I want to provide you something that's not wrong, and then just work into a little bit of an intuition for when you might use them. So what I'm going to do is, I don't quite know how much time do I have, Sandra?
So we actually at 12:30 we're supposed to have an hour break, so you can go a little bit longer. We can just do a shorter break and jump to the QA session after to the lounge to one of the booths.
Okay. So what I might do is I might just talk instead of showing some code just for a few minutes, and then I'll go over to the spatial chat if you want to explore it a bit further. Yeah, so what I might write a little bit of code. So because it is relevant to, so if I go there, hopefully you can see my screen with a text editor and all that. Here's a data type. It's a very straightforward data type. It's a product type. It's a product between strings and ints. So a person is a string and an int. Okay, so pretty straightforward. But there's what we're talking about here when we refer to optics. Actually, I just realized I missed the definition. Sorry. Here's the definition of an optic. Not very helpful if you've never heard of them before, but that's an optic. If you were to type that code in, you would have the definition of an optic. Not particularly helpful on its own. But let's try to get an intuition for it. There's the relationship here between a person and a string is that a person has one string and some other things that we don't really, we're going to sort of put aside. We just know that it's there. So basically there is some relationship between a person and a string to get down onto the field of a person. So if we just take the words that I said, so person has a string and some other things, and I just want to reiterate here that I've said an expression of this form. I've said X has a Y and some other things. The name of this relationship with respect to optics is called lens, right? So a lens is a type of optic. It's a specialization of an optic. The relationship when you have X has a Y and some other things is called a lens. Now, lenses get a lot more attention than they deserve, just like monads do, and that's only because they were discovered first. But there are other relationships. I'll see if I can just make one. Yeah, I'll just make one up. So sealed, trait, we've all seen this before. Let me remember what JSON actually is. I don't remember. It's like a Boolean, or it's a string, right? Something like that. And it's some other things as well, but blah blah blah. the question we have here is, with respect to this constructor here, what is the relationship between JSON and string? Now, it is not this relationship, right? So it is not JSON has a string and some other things. It's or some other things, right? So it either has a string, or it's one of these, or it's one of the other things. This relationship is called prism. So whenever you colloquially express this relationship, you are talking about a prism in terms of developing an intuition. And I'm conscious of time, so I'll just give you one more. So case class, I start running out of identifier names after person and JSON. Blah, S1 string, S2 string, and some other things, so on it. And the question we have now is, what is the relationship between blah and these two strings? Now, this relationship can be generalized to x has 0 or many y and some other things. Pardon me, where x in this case is blah and y is string. Now this, so we asked the question, what is the relationship between blah and string with respect to these two strings? And the answer to this question is called traversal. And these things, lens, prism, and traversal, are all types of optics. Now, what I'm saying to you here, or in terms of like practical application, what I'm saying to you is, if you ever find yourself, if you write that data type, you go to work tomorrow and you type, case class blah, two strings, and then your use case might be something as simple as make all the characters uppercase in both the strings. What you actually want is you want to take a value of this type, so val x equals, and make sure, write this thing. You're going to have a traversal, and then your use case is going to be val use case is x, and then it's going to be using that traversal to uppercase all the characters in those two strings. Similarly for lens, some people think of lens as like a pair of a getter and a setter. Yes, you can get a string out of a person using the lens. Yes, you can set the string in a person using the lens. However, there are hundreds and hundreds of other things you can do with a lens. And those hundreds of other things are the important bit. And in fact, when I was referring to the code duplication earlier, those are the things that I see duplicated over and over and over again. It brings me great dismay. So hopefully I've done a good enough job within my short time and given you just a little bit of intuition. I'm going to head on over to this spatial chat and we can discuss it further. That's all I've got. Thanks for your time, guys.